So as the first step of our presentation, we are going to talk a little about the concept of systems engineering and the whole basis of the course and of the topics we're going to talk about. So systems engineering is an interdisciplinary field. Um, it makes some tools of engineering and engineering management, and its main goal is to design, integrate, and manage complex systems. And these complex systems are seen in their whole life cycle. Um, Beside this, we can say that systems engineering gives space to a specific kind of engineer, the systems engineer. Their job is to evaluate and assess these complex systems, the systems that has many components and should be seen in a holistic way, um, and evaluate and assess the systems in a way that uh, they will reach the correct costs and performances.
Systems engineering provides guidance for the planning and realization of projects with the following objectives. First, minimization of project risks, as it improves project control by specifying standardized approaches and describing the corresponding results and responsible roles. It permits an early recognition of planning deviations and risks. Secondly, improvement and guarantee of quality. It ensures that the results to be provided are complete and have the desired quality. One more objective is the reduction of total cost over the entire project and system life cycle. The effort for the development, production, operation, and maintenance of a system can be calculated, estimated, and controlled in a transparent manner by applying a standardized process model. The last objective is the improvement of communication between all stakeholders. The standardized and uniform description of all relevant elements and terms is the basis for the understanding between all stakeholders.
We can summarize three topics which system engineering has emphasis on. The first is a top-down approach, which means you have your whole project or your whole system, and you make it a breakdown to get your smaller piece or your lower system or subsystems that you can have a direct handling over it. So this is a top-down approach. It's very common to use in system engineering. The second is an interdisciplinary approach. So that is, the more technical diversity you have applied in your project, the better is the understanding of all systems components. It's very common. It's very common to find different types of systems or subsystems with different disciplines. So the more diversity is your team, is your project team, is the higher the chance of success to identify and to get your system and most understand. And the third one is the life cycle engineering approach, which comprise 7 steps. Start at the project initiation when your stakeholder warnings, the stakeholder meetings. So what they need, what are the risk analysis, and so on. And going through the requirements, as I told you, what is needed for this project. Then the design. So after you get the needed, the project objects, you can propose a design. Then you go for implementation. When you get a prototype, you have a prototype generation, and then you can test it with your client or not. So you go to a trial environment, and so you can test your prototype. And after that, after you get your answer about your prototype, of course, you can make modifications. You can to improve it. After have your agreement about your prototype with your client, you can go to the deployment, which is you have the almost the finalization and almost you have your final product done. And then you have the maintenance, which is just to improve. You have the direct contact with the user, and then you can make improvements over the feedback. So this is a cycle. So after you have the maintenance, after you have your user feedback, you go again with your project initiation and go through the whole cycle again. So those are the three main topics or three main approach, which is very common to be applied in the system engineering. Okay.
With the intention of simplifying the process of implementing systems engineering, we can structure this implementation with the application of 5 pre-established steps. And those steps are: 1. Analysis of needs and management for the implementation of the system. It is from this analysis that the necessary data will be obtained to define the approach strategy, the necessary resources, and etc. 2. Functional analysis and resources allocation. This is easily observed in the paper because we are presented at the very beginning with the decomposition of a complex system into subsystems and the application of and use of simulations. Those simulations facilitates this task. And 3, design synthesis. With the possession of the data described earlier, we can obtain a synthesis of the system. 4. System analysis and control. This is easily seen in the paper from the passage model purpose, scope, and intended uses to passages 5.3, building confidence in model. 5. Verification. In the same passage, 5.3, the second leg of V is described and is responsible for the verification and validation of the model.
Systems analysis and control are related to the requirements analysis, functional analysis, and design synthesis. This is all part of the system engineering process. To have reliability in the model, it is necessary to verify and validate it. This confidence grows progressively as the model goes through verification and validation. The verification ensures that the model has no inconsistencies and that it was built according to the requirements identified at the beginning of the modeling or identified during the process. Verification means that the governing business rules have been identified and coded correctly in the structure, resulting in the correct replication of the behavioral references modes identified in the previous phases.
The definition of systems engineering, and it's really connected to the article we read, because the article talks specifically about the V model of systems engineering, a specific tool in this field. um, and we can define vModel, the vModel as a graphical representation of the system's development lifecycle. So it's a specific tool inside the field of systems engineering to help you in this lifecycle. Specifically in this article, we have an application in the modeling of systems dynamic of dryland salinity in the Murray-Darling Basin.
With correlation to the research paper where the V model of system engineering is used, it provides a path for improving the cost effectiveness over the entire life of the system from conception to retirement. Systems development life cycle is a process for planning, creating, testing, and deploying an information system. The systems development life cycle concept applies to a range of hardware and software configurations. There are usually 6 stages in this cycle: requirement analysis, design, development and testing, implementation, documentation, and evaluation.
In the article, a mix of concepts of dynamic systems and engineering systems with the verification and validation approach were applied. A flow sequence test was carried out to guarantee the integrity of the stocks and that the outflows do not precede inflows. So, first, the dimensional consistency was guaranteed by a software that performed the simulation. After each equation was analyzed individually, and last, a simple model was built without using complex technicalities, including multinational arrays. All of these procedures ensure that there was no inadvertent creation or destruction of flows, and uh, that the model was correctly.
In general, the first leg of V decomposes a very big problem in simpler situations to be treated or simulated, and this is done in a structured way, with the first part being the development of the system, the development of subsystems, and the development of LCI, lowest configuration item. This step in the process can easily perceived in the paper because there are steps that describe how the initial situation was decomposed into steps: requirement elicitation, model proposal, and model specification.
The left side of V represents the decomposition of requirements and the creation of system specifications. The right side of V represents integration of parts and their validation. Components are designed and then integrated to progressively improve performance and compatibility of all components of the system. The use of the V model provides a structured way for developing computer simulation models with a top-down approach for requirements elicitation, and it ensures that the computer model meets all the requirements and limitations elicited through a qualitative system dynamic and defined at the start of the modeling exercise. It also provides rigorous verification process.